Sorry.
Okay, so are we done with memory lab? Everyone's done with memory lab? Most people are done with memory lab? Are you done with memory lab? Okay, you're not shaking your head. Okay. All right, so it'll be very foundational for the final project. Okay. So your next week's lab is on HLS. HLS is high-level synthesis. And high-level synthesis is something that we like a little bit. It's not great, but if you know how to write good structural code that it knows how to optimize well, then it's great. But if you just give it default code and you don't understand how the HLS interpreter works, then garbage in, garbage out. Okay? So what high-level synthesis is it's a code compiler that uses C++ code, structural C++ code as inputs, and they give you VHDL on output. So rather than going through the process of coding your data path, your control, all of that, you give it the C code, and it gives you the FPGA code. So, but like I said, there are some downsides to this. If you are a expert, or you don't even really have to be an expert, but if you are knowledgeable and you understand hardware well, your design will always beat this design. So this is good for a quick and easy implementation, but it's not going to be the most optimized, might not be the most efficient, might not be the best performance. And the other thing is, if you don't understand what it's doing in the optimized part, and you just give it regular C code that it accepts, it's going to give you probably the worst design ever. You will see this in your lab. So the C code that I provide you for HD inference, which is what you're doing for your final project, you're going to feed that into this HLS tool, and you'll see that the architecture that it gives you at the outside is just the accumulator architecture. So the iterative architecture. And we talked about last time, if you have more data available, the iterative architecture is very bad, right? Doing one thing at a time. We want to unfold it. We want to pipeline it, right? So those are the downsides. But the upside is if you do know how to write the code that the tool can optimize well, you can get a better design out of it. And again, you'll do that in your next lab. So you'll make a small change to the code that I provide to you, and you'll see that the tool gets double the performance on the output compared to the code that you start with. Okay. But the basic functionality is, like we already talked about, going from C code to high-level state machine, right? That's the first process that the HLS code does. And then once it has this diagram representation of what the code is doing, then it can automatically generate the code for that high-level state machine. Right? So like We have structures for what a loop would look like. We have structures for what if statements, if else statements look like, while statements. The only thing that we have to make sure is that this C code is structural. So you can't have any pointers. So in terms of support from C and C++, the vast majority of these languages are supported by the HLS tool. And it's provided statically and defined at compile time. If it's not defined until runtime, like pointers, right? Pointers are dynamically sized at runtime. It's not synthesizable by the HLS tool. The HLS tool will not be able to give you outputs of a hardware design for that because it needs to know exactly how big things need to be, right? If it can be dynamic in size, it doesn't know how big it needs to be. So going along those lines, certain code must be changed. Dynamic memory allocation. You can't do this. No malloc, no dealloc, right? No dynamic memory size. You need to say that this array is going to be 10-dimensional. And that just goes back to no pointers. System calls, if you're doing print to the serial console. The hardware doesn't do that. Right? It's not going to change. So if you have any debugging statements, things like that in your code, you need to just comment them out. Or also if you're trying to access things like your application needs input-output from the user with keyboard or mouse, things like that, the HLS tool cannot do that. The HLS tool in general is not very good at coding for control things. It's very good at coding data flow. So if you have applications where you have this large algorithm that you're implementing in hardware, things like that, that's what the HLS is good at. The other thing is certain code should be changed for performance. So oftentimes code is optimized to get the best performance when running on a CPU or maybe a DSP or a GPU, right? Like you don't code a game to run on CPU if it needs to generate frames. You code a game to run on GPU, the optimal hardware for it. Yes? The same thing needs to happen with the HLS tool. If you are targeting an ASIC design or an FPGA design with the HLS tool, like we talked about at the beginning, you do not just give it the C code that is the baseline. You need to change the C code and recode it in a structural way that is optimal for the HLS tool to give you a better design. So this is your code that you are provided for next week's lab. This is the page file. This is inference study. So this is just defining certain things. Dimensionality is 1000. The number of iterations is 20, and the number of classes is 20. And then it's defining these types. And it's saying, I have an array A of this type, and there's 1,000 of them. This is what we mean by structural code. This is not an array pointer, right? It's going to be 1,000 in size. Same with B. It's going to be 1,000 inside. And then this is the actual implementation of inference. Okay. This is our looping variable. This is our intermediate variable to keep track of the counts. And all we do here is loop through all of the dimensions, right, of A and B, and count where they're matching. Right? This is what we talked about. It's just counting where these are matching. And then it returns the count. How many dimensions match? So that's inference. And this is structural code for this. But what you'll see is the HLS tool just directly implements this structural code. So when it sees this for loop and it checks one thing at a time, the hardware that it generates will check one dimension at a time. But we know we have all of 1,000 dimensions at the same time. So what you will do is, rather than checking one dimension at a time, you'll just change this code to check 2 at a time. And you'll see that the hardware that it produces is now checking 2 dimensions at a time, which is double the performance, right? So it's just kind of introducing you to what the HLS tool is, what it can do for you, what its limitations are, and how you can change your code in order to get a better implementation with the HLS tool. All right. And this is just more code that it's going to run. This is the main file. It has your arrays, and then your results are going to go into this 2D array. Let me change to the laser pointer. These are your 2 arrays. The results are going to go to these 2D arrays. And then this seed is set to 5 so that our results are always the same. This is just so we can check that after we make the change, that the result is the same as before we made the change, right? Because we want the results to be the same. Otherwise, our design is incorrect. Okay? And if we don't put a seed, because all of these values are being generally generated randomly, we won't have a reference. So we want to make sure that these random numbers that are going to be generated are the exact same. And then all this code is doing is looping through the samples, generating a new vector, and then here it generates a new B vector. And then after it's generated those vectors, it's going to loop through the classes, which are K, and call inference and get the number of matches for sample I, class K. Okay, yeah.
So all we're doing is basically SRAM is generating random numbers, storing them into the array, then we're checking which
SRAM is setting the seed. It's not generating random numbers. We're generating random numbers here.
Yeah.
RRAND, the RAND. Okay, generating random numbers here. This code, you will not touch this code. Okay, you will not touch this code. I'm just showing it to you so you understand what it's doing. Again, you won't touch this code either, the H file. You will touch this code. Specifically, you will edit this for loop and what's inside. This is the only place that you should touch. Okay? Because this is the core function, right? This is the inference function. This is what we want to create hardware for. All of this is just control, right? It's just going over different samples and the different class hypervectors. All right. So the other part that you will see is that it's going to save the results to this file, results.dat. And in the zip folder for this final project, there is this reference file called result.golden.dat. This is your reference result. This result.dat needs to be the exact same thing as the golden results.dat. This is the absolute path to the golden.dat. This is the absolute path where I had it. Right? You can see users, my username, JL1, my downloads. You will have to replace this with the absolute path where you put result.golden.dat. The result.golden.dat is provided for you. And all that this function is doing is, what's the difference between result.dat, which is the file that we just generated, and the golden? If there is a difference, then the test fails. If there's no difference, the test passes. Yeah.
Is this just a test from C code?
Yeah, this is the C code. After it passes the C code test, it will generate the same results by running the VHDL that it generates. It'll generate another file. It'll do the same test.
Okay.
And it is all done automatically for you. But it will tell you if it's wrong.
I thought it didn't do system. The VHDL, I thought it didn't do system calls.
Yeah, it runs the VHDL code and it outputs into a file. And then another process will do something like this.
Okay.
Right? So if you had system calls like this, where it's calling diff, inside here, you can't do that.
Okay.
But this is in the tester file.
Okay.
Right? So that is the high-level state, not high-level state machine, the high-level synthesis lab, which is the last lab that you'll do, and you do it next week. And after that lab, it's on to the final project. And part of the second part of the high-level synthesis lab is starting printing values from the Python code for the final project, so that you have that reference, and you can also have the class hypervectors and the query hypervectors that you can load into your design and test that is your design correct or not. Okay, and the reason that we input this into the high-level synthesis lab is all you're going to do in the high-level synthesis lab. It's step-by-step instructions. You're going to input this as is, see what the result is. Then you come back to this code. You change this code a little. You input it, see that the result is that it's 2 times faster. That's it. Okay. And then after you do that, it's on to printing the hypervectors from the Python code into your RAM VHD file. Okay. So this is one of the functions in the Python code. Python code is on Canvas. It's been on Canvas since the beginning of the semester. So, test. First thing it does, it takes the class hypervectors, makes a copy of them so it doesn't modify this variable, and binarizes them. the binarize, it's just going to make it
Binary.
1 and -1. Okay. Then we have this variable correct, that's going to keep track of how many of the test hypervectors we get correct. Here we're looping through the test hypervectors. And these are already binary. This guess is the class hypervector that had the most number of matches to the test hypervector. That's what check vector is. So check vector is your inference function. Okay. And then if the label for that test vector is the same as guess, that means we were correct. Right? So if we're correct, add 1, and we loop through all the tests, that gives us our total number of correct. Accuracy is the total number correct divided by the total number of testing samples. And that gives us our ratio, but multiplying it by 100 gives us our percentage. Okay, and then we'll just print that and return accuracy. So what do you need from this code? What do you need to print?
Accuracy.
Accuracy.
How do you need print accuracy? For your functional simulation, what are you going to load into your VHDL code? What needs to be in the RAM VHD?
Correct.
The hypervectors. Yeah.
What hypervectors?
That.
Yes, you need the binary class hypervectors. Okay. So this is one thing you need. What is the other thing you need?
We already have
Accuracy. The accuracy.
You don't need accuracy. What do you need? In order to actually do anything, I need the class hypervectors and what else? To perform this inference check in my high-level state machine that I designed for inference. Class hypervectors. And I need the test as well. Okay. There's 26 class hypervectors. Okay. There's your example of how to loop through the array right here. Okay. So just right here. For index and range length class hypervectors. And then for index and range length class hypervectors at 1 or the dimensions, because class hypervectors is a 2D array. Right. Each row is one of the class hypervectors. Each column is a dimension. So you're going to loop, you're going to have a double loop, and you're going to print out these class hypervectors. And then for the test hypervectors, you already have the first loop right here. You just now need a loop with the dimensions. And then here's your example of how to print. Okay. This is the only place that you should be changing code for inference to print values for inference. Okay. Only place. If you want to create helper functions, here's your example of how to define a helper function. Okay. So here's some information about printing. Your HD array is going to consist of 26 class hypervectors and 128 test hypervectors. So in terms of how many different cells do I need? If I have one cell for each class hypervector or each hypervector in general, then I need 154 cells. It's just 26 plus 128. So if you look at your example RAM file, it has 128 places that it can go to. 128 cells. So we need to change that to fit more. Okay. The other thing is each row needs to fit an entire hypervector. A hypervector is 1024 bits. Okay. Each one of these cells right now fits how many bits?
8.
8. And where is that defined?
STD logic vector.
8. So what does this need to change to?
1023 down to 0.
Yes. Right. And these hex characters, each one represents how many bits?
16.
One hex character. What's 5 in binary?
Those four, they're 4 bits.
Yes, 4 bits. 4 bits. 4 bits per hex character. Right. So what we need to do when we're looking through our hypervectors on the dimensionality part, we're going to iterate by 4. Okay. And then if we iterate 256 times, 4 times 256, I get my 10,024. The whole hypervector. So I look at the first 4 dimensions of my hypervector. What is the hex representation of those binary 4 bits? Where I'm treating -1s as 0s, 1s as 1s. So if my first 4 dimensions are -1, -1, -1, -1, my hex character that goes for the first position is
0.
0. Yeah. I loop back around. I go to the next 4 dimensions. I guess -1, 0. I'm not -1, -1, 1, 1, 1. My next hex character would be
7.
7. Yeah. Okay. So you're going to want to do that loop by 4, figure out what is the hex representation, print that character. And then for each one of your starting hypervectors, when you loop back around, you print X, you print the parentheses. And then when you start looping through the dimensions, you print the 256 hex vectors. And then you print a comma, start again. Because then if you do it that way, you run your Python code, you look at the output console, copy, paste, right? Rather than if you just printed out the hex characters and then you have this long string of 256 times 154 hex characters and you don't know how they're split up, you want to, when you're printing, split them up as you print, because you can write that into your code. And that's what I'm talking about here. You want to handle formatting when printing from Python rather than manually processing the hex characters after. Make sense? So that is part 2 of the next lab. Part 1 is the HLS part. Part 2 is by the end of that lab, you should have your new, rather than RAM array, you can call it whatever you want. Let's just call it HE array that has all of the values that you need to in order for your functional test to work. Okay.
What's a decoder? It's a decoder
What do you mean?
because we're changing it from Or are we just organizing, like we give just a mess of hex and you're just organizing it, um. Or is it a bunch of random binarized stuff and then change it to hex and organize it?
So you're changing this RAM array to fit how many hypervectors you need, and you're changing the size of them to fit the size of a hypervector rather than just 8 bits.
Okay.
And then you print out every single hypervector as a 256 hex character digit.
Got it.
And then when you load these values into your design, when you read one value, you read one entire hypervector. Right? Because before we were reading one 8-bit cell, but we're changing these cell sizes to 1024. So we'll get 1024 out. So you're going to need to change not just this part of the RAM VHD file, but also the input-output sizes. Any questions? Okay. The other thing I will tell you about is once you have all of your class hypervectors and your test hypervectors, and you have RAM VHD, and you start your design and you can simulate and you start getting results. Now, how do I know if my design is correct? On the waveform, I'll see that I'm loading in the hypervectors, right? And then I'll load in a query. And then once the query is loaded in, it'll go through my data path. And then at the end of my data path, it'll output a number 0 through 25, right? Whichever one was the maximum number of matches or the least number of mismatches. Yes? No? Are we not understanding that? What's the problem? Where is it confusing?
What's the query?
Query is you have 26 class hypervectors, and when you compare the query to the 26 class hypervectors, and you count the number of matches, you'll get an array of 26 numbers. What was the number of matches for this class hypervector? What was the number of matches for this class hypervector? And so on, right? And then the output that you select is the number that is the highest number of mismatches, right? The highest number of matches, I mean. I think I said mismatch.
You said, yeah, that's on.
Okay. The highest number of matches, right? And that's going to correspond to one of these class hypervectors. So what is the index of the highest number of matches? That's your output. So maybe class 0 means that it's A, class 1 means B, or so on. But you'll have that on your waveform, right? As output, you'll see 0 through 25 at the end of your data path. Yes? Now I need to know, is my design the same, giving you the same results as this, the code? Right? Because we have the same class hypervector, we have the same query. I'm trying to implement the same inference function. My guess should be the same. Understand? So once you have all of that done, then one thing, the next thing is print guess. If they're all in the same order, then my guess should be the same as this guess. Yes? And then when I check the next classified vector and I look at my waveform, my second guess should be the same as this second guess. And then you just check on that. So you'll just print out guess, is what I'm saying. It'll just be print, guess. Like this is just print, and this is a string accuracy. You'll just do print, string, guess. Okay? You can also just do print guess. It'll automatically convert it to a string. The only reason that this needs to be converted to a string explicitly is because we're trying to append it to the string. So that's how you're going to check your design. What's another way that we can check our design? I just tell you this way because that's what most people end up doing, most students. They like to do the manual checking. But what would be a better, more efficient way if you're going, because you're going to be doing this check probably how many times?
Well,
yeah. All right, is your design going to be correct on your first try? Is your design going to be correct on your 10th try? Probably not, right? So, and how long is the process going to take? Looking through the waveform, finding my first results, or even worse, maybe my first 5 are correct, but then it starts getting wrong. Then I have to check and find where is it starting to become wrong. Right, this can take many minutes. And say you do it 10, 20 times. It's turning from minutes to hours. But if I write the code for this, and I already have a template from Python, I just need to change it to C code in my test bench and read from the RAM VHD, or whatever you're going to call it, right? Then it can calculate for me what should be guess. And then my design just also outputs when it has an answer. Test bench checks that they're the same for me, prints out fail if they're different. So writing the code for this maybe takes 3 hours or something like that. I'm just putting a number out there. But it's very likely that if you're doing the manual checking every single time, if you add up all your time for manual checking, it's going to be greater than writing the code for that. But that is not required. That's what I described now is just how they would want you to do it in industry, because it's not just going to be you checking that your results are right. Say your project manager or someone in management will also want to see that your results are right. They're not always going to have the experience or knowledge of looking at a waveform. You're just going to confuse them. But if you have the console, it says test passed, then it's a lot easier to show them. And it's also a lot easier to pass on projects to other colleagues, right? Because if they make a change, they just run the test. If it broke, then they know that the change they made immediately was wrong, right? Rather than spending hours trying to figure out where it went wrong in the waveform. Generally, we all hate looking at the waveform, yes? It's hard. It's not what we're used to looking at, right? So if we can look at text printout on the console, it will be better, faster. It just takes a little bit more development time up front. Okay?
how do you know if your checker is right?
you can check your checker with this.
Okay.
Right? Because you always have this reference golden solution. And this reference golden solution, although it generates random things, it also has a seed. So it will give you the same results every single time you run. Okay. So that is your lab for next week. Okay, last lab. It's the same thing as the memory lab. No test bench is provided. Well, like I was saying, if you want to do it manual checking, all your test benches instantiates top level, resets, clock, maybe a done flag, right? Sets reset to 1, waits like 10 nanoseconds or whatever, sets reset to 0, waits until done is 1. Right? Your test bench can do that. And then you just have to manually check the waveform that your results are correct. I'm just saying that if you want to try and do a little bit extra upfront work, it could save you time in the long run. But I am open to whatever test bench design that you want to have. If you want to manually check, that's fine. You can manually check.
So out the our lab will do it to a file that we designate, whatever we name it, RAM.bhd or whatever.
You're talking about these printout things?
Yeah.
Yeah.
So I'll print to that, and then that is supposed to be checked to see if it's right or not through another function.
No. So RAM this, let's just call it HD array.
Okay.
So this HD array file is just to be read from. You don't store any results into it. So this isn't what you would check for if your results are correct. This is just a way to get the same data from the Python program into your VHDL design in the hypervectors. What you're going to check is the output of your data path, which is guess. Right? And you're going to check that that guess is the same as this guess. Okay. And one thing that is important is that you make sure that the index of your class hypervectors are the same as these class hypervectors. Because if they're different, like say you have them reverse, then your class hypervector labeled 25 is this class hypervector vector, which is labeled 0. Your guess is not going to match. You would have to know the conversion. But if you just keep them the same, then you don't have to know any conversion. Same thing for test hypervectors. Just keep them in the same order. Yep.
So we have some Python code that does its guess, and then we have our own VHDL code that does its guess.
And then we check.
How do you merge those two guesses? Or how do you filter between them? Like you said, compare them?
Yeah.
How do we go about doing that?
You look at the print for guess. You look at your waveform. Are they the same for the same hypervector?
But that's the long way.
That's the long way. Okay, so if you're talking about the automated way, you write C code in your test bench that will loop through HD array and calculate the guess.
So
And then-
that Python checker is converted to C code and that's put into the test bench?
Yeah.
Okay.
And then you can automate checking that that is correct by you print out a file just the guesses in a row, like each row is a guess. You have your checker in your test file, print out a file that is just guess in a row. And you do the same command, diff, right?
Mm.
Are they the same? Then you know that your checker is the same result as this code. And then once you know that, now you can just add into your code, check my design's result with the checker, and print out if it's wrong or not. I will tell you, no one has ever done this. Everyone has done manual checking, just so you know. Okay. And the reason is because there's only 128 things to check. Well, I mean, usually once you have the first 3 correct and the last 3 correct, then you check the rest, right? So it's not as long as it potentially could be, because I can tell you that the actual real data set has 6,000 or 7,000 samples that you would need to check. I just shortened it to 128 to support if you didn't want to do, if you wanted to manually check. Okay? Because I don't want to force you to do the other thing, because I know not many of you are very skilled with C yet, or even Python for that matter, right? And it might feel outside of the scope, but I just want to inform you that it really is inside of the scope of digital logic design, because we need to be able to efficiently check things. Because sometimes it's not feasible. Like, there's no way I'm going to manually check 7,000 results. I have to write the code to do that. Right? So just as a pre-warning, no one has ever done this before. The students at UCSD, even then, maybe 2 of them have done this before when I present this project. Okay? So don't feel that you need to, but I'm just informing you that that is the industry standard. And if you get a job in digital logic design, you will be forced to do it later on. Okay? So, and that's just me saying that manually checking is okay for now. Okay? All right. So by the end of this lab, everyone should have the HD array VHDL file. So everyone should be ready to start implementation of HD inference. Okay. And for the final project, you can select your lab partner, right? You can choose whoever you want to work with, so long as they also want to work with you. Okay, so that is today. On Friday, I am going to go over high-level state machine example, because next Wednesday is your quiz. I mean, on Monday, I am going to go over high-level state machine example. That is your last lecture from me. Okay? The rest of the time is for you to work on the final project.
4 weeks of no lecture.
I want to make sure that you do this final project, okay? The final project is what, 20% of your grade? 25%? You need to do the final project. So I'm giving you all of this time. This is the purpose. Okay.
Will you be available during those lecture times?
Yes, I will be here.
Okay.
Code for day is 108. I don't even think it's, oh, it is active. 108.